I'm excited to be able to share some of our work on reconstructing scenes from videos of propagating light. So to start off, I want to tell you about a thought experiment, one of Albert Einstein's thought experiments, where he envisioned a person standing on a train platform, and there's a train passing by. And right as one of the train cars passes by this person, two bolts of lightning come down and strike either side of the car. Okay? And now, to this person standing on the platform, it appears that these two bolts of lightning strike simultaneously. And then Einstein asks the question, what does a person standing in the car, moving with the train, observe? So clearly, the person on the platform, being equidistant from each bolt of lightning, and the bolts of lightning, the wavefronts of light, they travel to him at the same speed. This person sees the bolts of lightning strike simultaneously. But for an observer traveling towards one of the lightning bolts at relativistic speeds, the wavefront of light will actually close to him, will approach him, and reach him before the other. So this observer who's moving perceives one of the lightning bolts to strike first. And so in this talk, I want to build on this and ask two questions. The first is, can we capture and visualize light propagation from moving viewpoints as Einstein imagined? And second, if so, what can we learn about a scene by watching how light propagates through it? So let's take this first question. And to answer this, I want to show you this video. This is what we call transient videography at 250 billion frames per second. We captured this video of this Coca-Cola bottle by attaching a pulsed laser to one side of the bottle. And this laser sends out short pulses of light that propagate from left to right across this bottle. And we captured this scene using a special type of camera called a single photon avalanche diode, or SPAD, that records individual arriving photons with picosecond level accuracy. And using this camera lets us capture videos of this scene at hundreds of billions of frames per second. So we'll be able to watch light propagate in this case. And I want to ask, do you think, what will this look like? So do you think that the light that propagates from left to right, the wavefront of light propagating from left to right across this bottle, will reach this corner first, as observed by our camera, or this far corner first? So take a moment, decide what you think will happen, and then let's watch and see what happens in reality. Okay, so we can see the pulse of light here resolved by the camera, and we also see other interesting effects, light that refracts through the plastic of the bottle, through the water onto this plane below the Coca-Cola bottle. Light continues to propagate through the bottle until it focuses here at the cap of the bottle, and then this wavefront of light appears to start at the near corner, and then it propagates away from the camera towards the other corner before eventually light scatters back to the back of this bottle. Now, why did I'll play it back one more time in full here. So again, we can see the pulse focusing at the cap, wavefront spilling out across the ground, and then scattering back to the bottle. Now, why does light reach this corner first? Well, it's simply because it takes less time for light to scatter to that corner and reach the camera. Remember, everything is captured from the perspective of the camera, and it takes light a longer amount of time to travel to the far corner and then scatter back to the camera. So what we see, just like Einstein predicted, depends on where we are and how we're moving. Okay. So the answer to this first question is apparently yes, but actually it's actually no. We can't capture exactly what Einstein predicted would happen because this video is not actually captured by a camera moving at close to the speed of light. In fact, I wish we could capture that, but our laboratory equipment doesn't quite support that. So what are we missing here? In fact, if you have an observer that's traveling towards a wavefront of light, you might think that the light would appear to be closing to this observer at greater than the speed of light, at maybe the sum of the velocities at 1.3 times the speed of light. If you have two cars that are traveling and going to meet together, if you observe the velocity of the car that's coming towards you, it appears to be approaching you at the sum of the velocities, right? But that's not how light works in our universe. The speed of light is constant in every reference frame. So in fact, this observer appears light traveling towards him at the speed of light. And to accommodate this, space-time actually constricts and contracts to preserve the speed of light. So as you travel at close to the speed of light, space-time in front of you starts to contract so that the speed of light is maintained. And that's called Lorentz contraction. So this is an effect that we can't hope to capture physically. We can simulate it, and we, in fact, show some of that in our paper. But this is just one effect, actually, of a few relativistic effects that we can't capture. So we can't move at relativistic speeds, but we can capture videos of propagating light and observe some effects that, Einstein envisioned in his thought experiments, including these viewpoint-dependent effects. Now, we're not the first to capture videos of propagating light. Of course, this has been done before using a variety of other imaging modalities. For example, using street cameras, time-of-flight cameras, interferometric techniques, or SPADs, single-photon avalanche diodes. But as far as I'm aware, these effects haven't actually been captured from multiple viewpoints before, which would allow you to visualize how light propagates in 3D. We also build on a class of techniques based on neural radiance fields, or NERFs, and techniques that synthesize videos from novel, uncaptured viewpoints. And just to recap, maybe we're all familiar with this, but just in case, what is a neural radiance field? Well, this is a technique that takes in images or videos captured from a diverse set of viewpoints, and then it reconstructs appearance and geometry of a 3D scene by using a neural network to parameterize the color, so RGB color values, and the opacity or the alpha value at every point in this scene. And then once you've learned this reconstruction or optimized this representation, you can render an image or a video of this scene from any viewpoint using what's called the volume rendering equation. And that's simply a rendering equation that takes as input the color and opacity at every point. And so a neural radiance field is really a kind of colorful cloud that we optimize so that rendered images or videos from this representation are consistent with our captured data. And once we've had a chance to optimize it, we can achieve pretty nice photoreal image quality. But these are really just colorful clouds. That's how I think of them, how I think of this representation. But we're in a bit of a different regime than the conventional NERF or neural radiance field type reconstruction, in that we actually need to account for the speed of light in our representation because we're imaging that fast. So I'll show you how we can synthesize novel videos from novel viewpoints of light propagation. The method that we use to do this, which involves a new type of neural field representation, and we demonstrate this on experimental data by capturing a new data set. So how do we do this? This is an illustration of our experimental setup. We use a single pixel, single photon avalanche diode that observes the scene through a pair of scanning mirrors, and we synchronize our SPAD with a pulsed laser that sends out picosecond duration pulses of light into the scene millions of times every second. And for every pulse that we send out into the scene, we have a chance at detecting with our SPAD a single photon. And when that happens, the SPAD marks the time at which the photon arrives with respect to when the laser pulse was emitted, and it bins those photon timestamps into a histogram. So this is a histogram of the photon counts, which represents a kind of statistical average of how much light is arriving to our sensor over picosecond time intervals. Or in other words, you can think of this histogram as a single pixel out of our from a captured video of light propagation. And after scanning the entire scene, we can recover a video of propagating light from this viewpoint. And then we repeat this procedure multiple times from different viewpoints to build up an entire collection or corpus of videos of propagating light from different viewpoints. Okay, now there's something interesting that's going on here. So let me highlight a couple of these videos and let's zoom in on them and see what these look like. So do you notice anything different between these? So look, for example, at this wall here, and notice how light propagates down and to the left. And this same wall, observed from the other viewpoint, light appears to be propagating differently, right? So why is that? Well, it's because there are different distances to every scene point to our camera, right? So as we move the camera around the scene, the appearance of the scene also changes because our camera is in a different reference frame. So transient light transport is in fact viewpoint dependent. And because of this, it's not trivial to just apply a neural radiance field type method off the shelf. We actually have to model and account for propagation delays of light from every point in the scene to the camera. And what's more, we also want to account for complex light transport effects like diffraction and the refraction and light propagating through participating media. So how do we do all this? Well, we build on neural radiance fields and use much the same rendering method, but with a fairly simple change. We reconstruct a 3D scene by placing cameras in the scene at the location of the captured the viewpoints of the captured measurements, and we cast a ray from the camera into the scene, and we sample points, 3D points along that ray. And at every 3D point, we predict an opacity value or a density, just like with the standard neural radiance field. But instead of predicting a color value or radiance at every point, we predict what we call a per sample transient. This is a one-dimensional waveform that gives us a time-resolved view of the intensity of light coming back to our camera from every sample location along the ray. So for every sample, we have one of these 1D waveforms. And remember, we also have the predicted density values for each sample. We can explicitly shift these samples because we know the distance from our camera center of projection to the sample location, can calculate the speed of light time delay, shift these 1D waveforms by that propagation delay to model it, and then we simply composite these together using volume rendering, just like with the normal neural radiance fields. And this whole representation can be optimized by just minimizing the difference between what we render and what we captured. And then, once you've optimized the representation, you can render out videos of propagating light from novel viewpoints by simply placing the camera at some location in the scene, rendering out the video, sampling the time frame that you want to show, moving the camera to another location, sampling the next frame in time, and so on and so forth, so you can generate these videos of where the light is propagating and the camera is moving together. Okay, so now how did we do this in practice? Well, we built a hardware prototype, looks like this. This gantry was actually probably more than 20 years old. There's another faculty member in our department who wasn't using it, and it was in an old office somewhere, and I dusted it off, and we found how to connect to it over the serial interface. And at first we couldn't figure it out, but it turns out that the company that produced the driver for this, which is like 20-something years old, is still active. I emailed them, and within an hour they'd gotten back to me. So this is really just top-class customer support. So it still works, and we used it for this project. So what is this? There's a rotation stage, and we put the scene we want to capture on top of this stage, and then we mounted rigidly to this rotation stage a fiber that's connected to this collimator, and we needed to fiber couple this so that you could move the light source with the rotation stage. So we had a laser that couples out to free space, but if, it's difficult to figure out how you would move that free space laser with the scene as it's rotating. So we fiber coupled it, connected it to this collimator, and that illuminates the scene. And it's stationary with respect to the scene. And then we put our scanning SPAD system on this elevation arm, and this allows us to scan the scene in azimuth and elevation with the light source fixed in position. So it's like you're moving the camera around the scene and the light source is static. So this is a time lapse of what it looks like to capture the data. This is sped up by quite a bit. It takes about 20 minutes to capture a video from each viewpoint, and you capture many viewpoints, so the entire procedure, it takes about a day to capture the data set for one scene. So this is not a quick procedure, although we had long exposure times to try to capture pretty clean videos. So you could perhaps speed this up if you're willing to tolerate some noise. Okay, so now what does this look like? I'll show you a few other results. And the way that I'm showing these results is to take the transient video, this is in simulation, what you see on the right, and composite that on top of an integrated video or an intensity image. And we find that this type of visualization lets you see a bit better what's happening in the scene. You can place where the light is propagating in the scene better. So I'll show all the results like this. Okay, so here's another captured scene. This scene has a mirror in it, has a statue and a few other objects, and I'll play back the video. In this case, our laser source, the pulsed laser, is illuminating a diffuser to create a point-like source of light, and so what you see is a wavefront that propagates through the scene. So here it is. What's interesting here is that as the camera moves, you'll see that this wavefront on the left appears to be frozen. Why is that? It's because the camera is actually moving with the wavefront of light. So if the camera is moving with the wavefront of light, there's basically no change. In fact, this is not precisely physical, what you would see in reality. But here, the speed of light is basically constant. You can move the camera at whatever speed you like. So if you move it too fast, then light will actually appear to propagate backwards in time. If you move it, the camera towards the wavefront, light will appear to propagate to you faster, right? So this is an artifact of how we move with the wavefront of light. At this moment, we also see light reaching the corner of the statue. So the statue lights up, the other objects light up, and then a fraction of a nanosecond later, we see the reflection of light in the mirror. And why do we see that later? It's because, of course, it takes light a longer amount of time to bounce off the mirror and come back to the camera than to directly reach the statue and come back to the camera. And then we see some other interesting indirect light transport effects as light bounces around in the scene. Okay, let me show you another result here. So this was a bit more work for my graduate student. He put together a tank of water and he submerged a mirror and a diffuse reflector in the tank. And now we have a laser that's sending a beam, a train of pulses through the water. We added a little bit of milk to the water so that some of the light would scatter out to our camera. And okay, let's see what happens. So you see the pulse of light enter the tank, bounces off of this mirror, you see the specular reflection, and then the pulse looks dimmer here. So why is that? As the camera moves behind the pulse of light, it appears to fade. This is actually directly visualizing the bidirectional scattering distribution function of the participating media. That is, the function that describes how light scatters, in what directions light scatters in this murky water. So turns out that water with a little bit of milk in it is predominantly forward scattering. Most of the light is thrown in the forward direction of propagation, and there's a lot less light that scatters back in the backwards direction. So if our camera's behind the pulse, it appears a lot dimmer, right? And then we see the diffuse reflection off of this surface, and the rest of the propagation. So maybe we'll play it one more time. Yeah, it's kind of fun to see how bright that specular reflection is, and then see the other reflection. And you can see that diffuse lobe of light come off of the diffuse reflector as well. Okay, here's another example in the tank of water. We put a diffraction grating here. A diffraction grating is an optical element that splits a beam of light into multiple different beams through diffraction. Let's see what this looks like. So as the pulse hits the diffraction grating, you can see it separate into the different diffraction orders. So we see the 0th order, which is the light that propagates straight through the diffraction grating. 1st and 2nd order, these are a bit more faint. And then you can see even a little bit of the higher order diffraction modes. And these propagate through outside the tank and scatter outside as well. Okay, and here's one other scene that I want to capture. And this scene is interesting because it has a candle in it. And candles, most of the brightness of the candle is actually due to light that enters through the surface of the candle, scatters around, and then leaks out over time. So candles appear translucent because there's a lot of subsurface scattering. And we can actually see that directly in these videos. So I'll play back the video, and see the wavefront of light propagating through the statue. It lights up the surface of the candle briefly, and then you see the candles glowing for a little while because of all that light that's bouncing around in the subsurface and then leaking out over time. And of course, you see the reflection on the back wall, and then these indirect reflections of light bouncing around afterwards. So you can imagine that this could be pretty interesting for not just visualization, but we can actually tell a little bit about the material properties of objects in the scene based on how they interact with the propagating light. So I think we have an answer now to the first question. It's partly yes. Of course, we can't visualize relativistic effects, but we can capture and see a lot of what happens as light propagates through a scene in 3D. And because we can do this, the natural question is, well, what can we learn about a scene by watching what happens as light propagates through it? In these few examples, you've seen a few things, right? We can learn a bit about material properties, what stuff is made of, by how light interacts with it. Does it directly scatter off the surface of the object? Is there subsurface scattering? What are the scattering properties of participating media? How much light is reflected out in each direction? You saw that with the tank of water. What other things can we discover? Well, the most common scene property that we recover with this type of data would be geometry. So really, all conventional LiDAR systems are operating in this fashion, where they emit a pulse of light out into a scene, and they measure the light that scatters back directly to the sensor. And so in this case, the sensor records time-resolved intensity incident over time. And you see a peak in the measurements at the time at which the backscattered laser pulse returns. And based on this speed of light time delay, you can work out the distance to the point in the scene. And then by capturing, repeating this procedure for many, many different points in the scene very quickly, you can capture what's called a 3D point cloud. And this is a representation of the geometry in the scene. It's very useful for things like self-driving cars, because the car can now tell what's around it and hopefully navigate down the street while avoiding any obstacles and pedestrians and other cars and so forth. But it turns out that all current LiDARs that return this point cloud representation, they're actually discarding most of the information in the measurements. They're just taking that direct reflection of light, or trying to capture the direct reflection, and they ignore indirect light and other light transport effects. And in fact, LiDAR systems will fail when there's too much indirect light and when there's participating media like fog or dust or rain or snow. So perhaps we could do a bit better if we can model not only the direct component, but also the indirect component of light. And we can do this by through a physically based model of light transport using what's called the time-resolved rendering equation. And this is an equation that we can model and invert to recover geometry and other scene properties from direct and indirect light. So what is this equation? It gives us the outgoing radiance at a point in the scene as a function of the integral over the incident direct light at that point. So this would be the light that is emitted, for example, from our LiDAR system, goes to that point and comes directly back to our sensor. Also the incident indirect light. This could be light that perhaps hits this point or interacts with other scene points, bounces around before it returns, scatters back into the point, as well as some other terms that include the surface normals, the geometry of the scene, and the direction of the incident light. So we can, I won't get into all of the details of how we do this, but we can develop a differentiable, physically based model of the time-resolved rendering equation and optimize that physically based representation by, again, just minimizing the difference between what we render and what we capture, just as before, using a multi-view collection of videos of propagating light. And then what we can do is recover geometry. So what I'm showing you here is the output of a model that only captures direct light. And you saw the video of light propagating through this scene. There's a lot of indirect light, both from the candles, light that scatters off the statue and bounces off the surface, light that bounces around in the background. So if you only have a model of direct light, it turns out that this neural radiance field type representation puts a lot of stuff in the volume to try to model what it sees. But since it can only use direct light transport, it recovers an incorrect model of the geometry. If we model all of this using the correct physically based model, we can do a lot better. What's more, we can synthesize videos of propagating light with lights at positions that weren't captured. So if we have a model of the scene geometry and the reflectance parameters and everything else, then we can place lights in the scene at different positions and see what would happen if we illuminated the scene from those light sources. We can also automatically decompose the light transport in the scene into its direct and indirect components. So in the direct case here, you see the bright direct reflections of the green light on the side of the statue. You also see the shadows that are cast by our direct light source positions. And you can see the indirect lighting components. The candles, a bit difficult to tell here, but the candles are actually brighter than in the direct case. And you can see these indirect reflections of light at the corners of the scene. Here's another scene where this is maybe a little bit more clear. We can synthesize videos of light propagating from novel viewpoints. This might be interesting if you want to simulate what a LiDAR would capture if you placed it at other positions in the scene. Maybe you want to have synthetic data or pseudo-synthetic data to train your self-driving car. We can recover pretty nice geometry of the scene and again decompose light into its direct and indirect components. And we can do this also for light source positions that were not captured and relight this scene. Okay. So those are some things we can learn about a scene as we watch how light propagates through it. We can get the geometry from both direct and indirect light. We can do better than existing LiDAR systems that are only using direct light. We can recover perhaps material properties by decomposing light transport into its direct and indirect components. And what else can we do? So we have a few ideas for what's next. And yeah, if you have ideas, I'd love to hear that as well. And we're open to suggestions. So one thing I'm very interested in is using this type of data to image through scattering media. Our current physically based model does not handle participating media. We're working with a time-resolved rendering equation, but we need to upgrade that to use a full model of radiative transfer to accurately model light interactions with participating media. But this, I think, could be very interesting because we already saw that you can, just by visualizing the light propagation, get a good sense of how light is scattering out from a given point in those examples with the water tank. If you could do this optically, perhaps you could have applications such as biomedical imaging where you can see into a human body, or in this case, this is a technique called photoacoustic tomography developed by Li-Hung Wang, where they're imaging slices of a mouse body. This is done using ultrasound, but there are reasons that you'd want to do this using only, this is done using a combination of ultrasound and optics, but there's a reason why you'd want to do this with an only optical modality, because optical absorption actually gives us other cues about blood oxygenation. We could perhaps tell glucose levels, tissue composition. You can use markers of optical absorption to detect cancer, to tell water content. So if you can image into the body using optical signals and invert the scattering that happens, that could be extremely interesting for biomedical imaging. There could be other modalities we could use this for. I mentioned advantages over conventional LiDAR, biomedical imaging. What about, I think some of you are working on non-line of sight imaging, imaging around occlusions using indirect light transport. Maybe you can go further in estimating material properties. We have a model for the reflectance of, actually recover a model of the reflectance of objects in the scene, but perhaps analyzing that and understanding that better would allow you to do segmentation or higher level computer vision tasks and perception. In terms of non-line of sight imaging, I'll just show you briefly an example experiment that I captured now. This is a few years ago. But we built this non-line of sight imaging system here. There's an occluder here, and we're trying to capture what this scene looks like. And so from the perspective of the imaging system, we can only illuminate and image the side of this building. Some of that light bounces off of this building, scatters to these objects. Okay, you can see the reflections of light on the side of the statue and the arms. Some of those photons actually scatter back to the side of the building and back to our imaging system. And our imaging system captures a video of propagating light or the light that scatters back to the visible surface. So you see these ripples here. Those ripples of light are from the hidden objects. They actually tell us quite a bit about the geometry of the hidden scene. So by modeling and inverting this specific case of light transport, light reflecting off a planar surface to these objects and back, we can recover hidden geometry. So this is a volumetric voxelized representation where the brightness of every voxel tells us something about the albedo or the brightness of the hidden objects. And perhaps by using the time-resolved rendering equation and the techniques we've been developing, including viewpoint diversity, capturing a scene from multiple viewpoints, you can do this type of non-line of sight imaging in far less constrained environments where we don't assume that there's a planar wall or relay surface that sends the light to the hidden scene, and where we don't have to scan the entire large patch of this hidden scene, but we can simply basically capture LiDAR measurements from a few different viewpoints and recover a much more complete geometry that includes objects outside the direct line of sight. So perhaps we can make these techniques much more practical. And the last point I want to touch on is this idea of imaging with individual photons. So the measurements that I showed you were captured with a device called a SPAD that timestamps incident photons individually. Thank you. The videos that we captured required pretty long exposure times. But what if we could push this to use very short exposure times, and rather than using a single pixel sensor, use a sensor array? So this is a camera we have in the lab. It's a single photon camera. It has 512 by 512 array of SPAD detectors, and we can capture, it captures binary images, like shown here, where the value of every pixel is either 1 or 0, and that indicates whether a photon was detected or not in that binary frame. We capture these very fast. It reads out about 100,000 binary frames every second. And we'd like to use these binary frames, which could be captured in extremely low light conditions. The device is very sensitive to individual photons, to recover clean images. So we actually want to model the likelihood of observing this image given the photons that we actually capture. And perhaps we capture even fewer photons. So we're operating in extremely low light conditions. Or perhaps we don't capture any photons at all. Can we model the likelihood of seeing this image? Well, this is where generative models come in. So this is an output of a video generation model that one of my students, Sherwin Bahmani, has been developing over the last few months. And what's remarkable about these models is they give you photoreal, very high quality videos of scenes just from text. You can tell it anything, and it shows you an astronaut cooking on a fire in front of some ducks, cats playing chess, or even a cat painting. And what I love about this one is you see it gives the cat another paw so it can hold the paintbrush. But we have these extremely strong priors over natural images and videos, and we can use them to model the likelihood, perhaps, of images given photons. So this is some simulated photon data. These are very early results. This is what the scene actually looks like. So it's perhaps a bit difficult to imagine from these sparse photon counts what the actual scene was, but by fine-tuning an image generation model, we can get actually a reasonable output from these very noisy images of what the scene looks like. Of course, it doesn't get the texture perfect, but in terms of semantics, it can perhaps recognize that there are cars here in this parking lot, that this area is a road, and maybe it makes this ultra low light data usable for downstream perception tasks. Maybe you have a robot that needs to drive down the car in very, very low light, and it's traveling fast, so you have to operate at a high speed. So perhaps we can use single photon cameras to overcome fundamental obstacles in low light, high speed imaging by leveraging generative priors. And this, again, could be very useful for robotics, remote sensing, perhaps even for self-driving cars. And so I want to leave you with this idea that there's more to what we're capturing. There's more to LiDAR than a 3D point cloud. And we can now, using emerging sensor technologies, combining them with the right light sources, capture videos of light propagating through a scene, which are extremely rich in information, and which we can potentially use to solve inverse problems that we haven't been able to tackle before. So with that, I want to acknowledge collaborators on this project, in particular Anug Malik and Ben Atal, who are leading the two research projects that I discussed, as well as Matt O'Toole at CMU, Kyros Koutolakos at UToronto, Gordon Wetstein at Stanford University, and Noah and Ryan. So thank you very much.
Thank you, David, for the nice talk. So let's have some questions coming from the audience.
Thank you for your time. It's fascinating.
Thanks.
Like all this computational imaging work from your group is just so fascinating. So I guess my question is, I think if you can do this on like fogs and water, as you mentioned for you, that would be really interesting, right? So there we could come up with better models than what we have today. But would there be a possibility where you could really build a large-scale data set of all these so that we can use AI to model those interactions?
Yeah. So how do we bring AI into these inverse problems, basically? So we'll never have data at the same scale as images and video. Even video, we don't have data at the same scale as images. So images, we have billions of samples. Videos, we have millions of samples, maybe. And people in that domain have developed clever tricks to leverage images, pre-train on an image generation model to do video generation. They've mined out video now. I don't think we'll get to that scale at all with these systems. And in fact, one of the challenges with working with SPADs is that these are prototype devices. This is the data I showed you are maybe the only data sets that there are that can capture light propagation in this fashion from multiple viewpoints. That said, I think a lot of what we want out of a prior is the same as what image and video generation models give us. We're still working in the optical domain. We're still working with everyday indoor scenes and objects. So what I'm hoping is that with limited data and some fine-tuning, or there may be other techniques, you can still leverage priors over natural images and videos for these more for emerging sensors and regimes where you just can't hope to capture data at the same scale. So that's what I'm currently betting on. And maybe there are other ways to do it, but I think we have to leverage these existing models because we just can't capture the data at the same scale.
This is a very low-level detail question about the equipment.
Yeah.
On your experiments, how strong was the power of the lasers?
Yeah, so the laser we were using was it goes up to 1 watt actually. So the non-line of sight experiment that I showed you, the outdoor setting, that was maximum power. That's not eye safe, and you wouldn't. I don't think it would burn you or anything, but you don't want to get it in your eye for sure. And you could tell how bright that was, right? How it was illuminating the side of the building. That was full power. In these experiments, we didn't. That would saturate the detector if we used it at that power. I think it was about 50 to 100 milliwatts. Still quite a bit of power, but not to that level. Yeah.
Okay, thank you.
Also, there are losses as it goes through the fiber and in the collimator. So.
Hi, thank you for the great work. And what I wonder is that can we also model some the scene with more detailed or complex properties, like scene? Can we also accurately model the scene with like a subsurface scattering or some complex BRDFs? Or can we also model this scene through the physically based rendering equation?
Yeah. So how do we model complex scenes with the physically based rendering? So we can model these scenes. I showed you the example scene with the statue and the candles. We can model that just fine in terms of synthesizing novel views and capturing the subsurface scattering. But we're not. We're using a kind of hybrid approach. So we're not actually modeling a spatially varying bidirectional scattering distribution function on the surfaces of the candles, for example. What we're leveraging is what's called a radiance cache. So a radiance cache gives you the outgoing radiance at every point in the scene in every direction. Well, that's exactly what a NERF is, right? So if you want to model indirect light without having to do recursive path tracing, which is extremely expensive and basically impossible to optimize through for captured data in a practical amount of time, you need to use a radiance cache. So we basically combined a physically based model, reflectance functions. We model direct light analytically with a radiance cache, which is basically the neural radiance field that I showed you in the first part of the talk to model indirect light. As well as some learned reflectance functions. And we combine these two, and that's what we use to model the time-resolved rendering equation. Now, the next step is probably to do as you suggest, which would be to constrain a bit more the radiance cache and try to learn try to learn explicit models of reflectance at every scene point. We do that for the surfaces that are visible, but we don't do that for the indirect light. Yeah.
So I'm not in the computer vision field. I'm doing some medical image analysis, and when I look at your like a presentation, it was very, very interesting. So just one curiosity. So can we use sound to visualize the image? Because in the like a hero movies, someone who has a blind can like visualize using the sound in the movie. But when you look at your like work, maybe it can be possible to do that when using like a indirect like reflections using that method you did in the 2019. Yeah, can we do that?
Yeah, that's interesting. Probably. I did once do a project where I built the thing is if you want to have a video of sound propagating through a scene, then you need, probably a fairly large microphone array to get the spatial resolution. And, but yeah, you can probably do this. In fact, I did build once a microphone array, just a 1D array, and did some scanning. I had an array of microphones and an array of speakers, and I did some non-line of sight imaging with that. So I think in the same fashion, you could probably use even a similar neural rendering model. You could do, maybe, you could make videos of sound propagation. I don't see anything fundamentally stopping that. Yeah, that would be interesting.